Okay, so for our next part in that lecture series, we're going to be going on to Hamiltonian mechanics. And before we get into the Hamiltonians and Hamiltonian formulation of mechanics, we need to just take a step back and look at energy in general. So we spent the last good while looking at conservation of momentum, and we've kind of forgotten about conservation of energy. Well, you might think that with our new skills and our new discoveries in comparing symmetries and conservation laws, we might be able to get something out of there for conservation of energy. And you'd be right. So when we were talking about conserving momentum, or momentum being conserved in a system, we were talking about taking that system, translating it in space, and see if it's invariant under that translation. And if it was, then the total energy or the total momentum in the system will be conserved. So we have to do a similar thing this time, but instead of translating our system in space, we translate that system in time. And if the system runs in the exact same way, it's said to be invariant under time translation. And that's how we'll get our conservation of energy. Okay, so if we were to have a look at our conservation of energy, and when a system is invariant under time translation, we have to look at that system's Lagrangian again. And we'll come to find that if the system is time translation invariant, this means that the Lagrangian will have no explicit dependency on time. So to kind of show what I mean by explicit dependency on time, let's have a look at an example of Lagrangian. Let's say we'll have a look at the harmonic oscillator. So the harmonic oscillator, we'll remember, is a system where a particle will oscillate along one axis with some kinetic energy, T, equal to a half mx dot squared, and some potential energy, V, which is equal to a half kx squared. And this is taken from our idea of the force being F equals minus kx, and our definition of potential energy and force, or a connection between the two, rather. So when our Lagrangian L of the system, T minus V, is equal to a half times mx dot squared plus or minus kx squared, we can say that this Lagrangian has no explicit dependency on time when m and k are both they're both constant, right? But if we were to say that instead we had some Lagrangian equal to a half mx dot squared minus some k, which is a function of t times x squared. Now the Lagrangian will have an explicit, because it has a function of time in it, then it'll have some explicit dependency. So the way that we were writing this before, and the way that we went through this in our more in-depth derivation of the Euler-Lagrange equations, was we wrote the Lagrangian L to be a function of some qi, some q sub I dot, and t. And we were using this general form of Lagrangian to find our Euler-Lagrange equations. Okay, so now that we have our general form of a Lagrangian with some explicit time dependency, we'll say qi dot, and t. Right, so let's have a look at how this will change when we take the derivative of the Lagrangian with respect to time. So if we had, say, dl dt, well, we'd have to take a sum over all I of the partial derivative of the Lagrangian with respect to q sub I times partial derivative of q sub I partial t plus partial derivative of the Lagrangian with respect to q sub I dot times the partial of q sub I dot with respect to time. Now we have this part here. This is what we were used to before when we had a Lagrangian with no explicit time dependence. But if we do have an explicit time dependence, we also have to add another term at the end, which is the partial derivative with respect to time itself. Okay, so now that we have this, let's have a look at the different terms. Well, we'll notice that this term here is the derivative of a coordinate with respect to time, and so that's nothing more than q sub I dot. Similarly, we'll have here the derivative of a velocity with respect to time, so that's going to be q sub I double dot. And now let's have a look at our other two terms here. From our Euler Lagrange equation and how much time we spent over that, looking at that, we'll realize that this term here, dl dqi dot, or sorry, dl dqi will be some pi dot. And our final term inside the summation will be dl dq sub I dot. And this will be our momentum conjugate p. Right, so now we can rewrite our derivative of Lagrange with respect to t as the sum over I of p sub I dot times q sub I dot plus p sub I times q sub I double dot plus dl dt, or the partial derivative rather. Okay, so now if we have a look at this, we can kind of, this term here in the summation, our i's, we can see that this is just the power rule for derivatives. So we can group this together and we'll get that this is the same as the sum over I of d dt of p sub I times q sub I dot plus the partial derivative of the Lagrange with respect to time. And again, assuming everything is well behaved and continuous, we can swap these sums and derivatives around. And so we'll get that the derivative of the Lagrangian with respect to time is the derivative of the sum over I of p sub I times q sub I dot plus the partial derivative of the Lagrangian with respect to time. Okay, so now that we have this, let's define a new term. So just before we move on though, we'll realize there if there's no time dependency or explicit time dependency on the Lagrangian, this will go to 0 because the principle of conservation of momentum. Okay, so let's define a new h, which is going to be equal to the sum over I of p sub I times q sub I dot minus minus L rather. So this is our term that we're going to be calling the Hamiltonian. So we'll have a look and see, and we might recognize this from somewhere that we covered before, but because this will represent the total energy of a system, usually anyway. So when we were talking about energy towards the beginning, I used the H to denote the total energy of the system, and this is really Y. So now if we find the H dt, we'll get that this is d dt times the sum over I of p sub I times q sub I dot minus dl dt. But we know from this equation down here that this will be equal to the derivative of the sum over I of p sub I times q sub I dot minus the derivative of the sum over I of p sub I times q sub I dot minus the partial derivative of the Lagrangian with respect to time. Okay, and we can clearly see that this term and this term will cancel out. And so we'll find that the derivative of the Hamiltonian with respect to time is equal to minus the partial derivative of the Lagrangian with respect to time. Right, so this is kind of a key, actually it's a quite key equation here that relates our Hamiltonian and our Lagrangian together. And so we can test this out and show that our Hamiltonian really does give us the total energy. So if we work down here and we'll say that we have, I'll just draw us out a little box here. If we have some Lagrangian L, which is going to be, say, a half mx dot squared minus some v of x, well, we only have one direction, or we only have one dimension, so we'll use our definition here, and we'll say that this means that h is equal to the sum, but there's only going to be one, so that's fine, over I, and our only direction is in the x direction. So this will mean the momentum in the x direction times the velocity in the x direction. So this means we'll have mx dot being the momentum times x dot minus the Lagrangian, which is a half mx dot squared. The minus will carry through, and we get a plus v of x. All right, and then expanding this out, we'll get mx dot squared minus a half mx dot squared plus some v. 1 minus a half is just one half, so we'll have that. Therefore, the Hamiltonian is 1/2 mx dot squared plus v of x, which is our total energy. Okay, so now that we have our two equations here, these are very our definition of the Hamiltonian and our connection between the Hamiltonian and Lagrangian derivatives, we can have a look at another example. So let's have a look at the example of a little bit of electromagnetism. So if you're not too experienced, it doesn't matter too much, but it would help. But let's say we have a charged particle moving in a capacitor, and the capacitor, therefore, will have some electric field, like so. Right. So if we have some electric field, if we have some electric field epsilon, we know from electromagnetism, and don't worry if you haven't gone over this or haven't seen it before, that the potential energy of the particle in this will be equal to epsilon times x. All right, so now that we have our potential energy and we have our kinetic energy being just a half mx dot squared, we can write this out as an example. So let's have our L equal to 1/2 mx dot squared minus epsilon of x, or epsilon times x rather. Okay, so now if epsilon is constant, so if the capacitor is fully charged, then we'll have that the Hamiltonian h is equal to a half mx dot squared plus epsilon times x. Right, so our partial derivative of the Lagrangian with respect to time will be 0 because there's, so then we have the HTT is equal to minus the partial derivative of the Lagrangian with respect to time. And because there's no explicit time dependence in there, we know this is 0. And so when our particle is moving in a fully charged capacitor, its energy will be conserved. Perfect. But instead, let's say that we had our capacitor charging, for instance. So our electric field wasn't constant, it was increasing. So we'll have, therefore, that the Lagrangian L will be a half m x dot squared minus some epsilon of t times x. And therefore, our Hamiltonian will be 1/2 mx dot squared plus epsilon of t times x. All right, so this would mean, therefore, that dh dt, so how much the total energy in our system is going to be changing, is equal to minus partial L, partial t, which the first term won't go into anything, and so we'll get minus, or our minuses will also cancel out, so then we'll get epsilon prime of t times x. So this now depends on our electric field, and so when our electric field becomes a maximum, when it's charged, our derivative will go to 0, and we'll have our original condition. So this means that our total energy of the system isn't being conserved. But that doesn't really fit in with our knowledge of physics from beforehand, that energy as a total must be conserved. And so you might be thinking, well, where is this energy coming from, where is it going, etc. And that's because we have an answer to that, and that's because we're not really thinking as a system as a whole. Because this energy is really coming from the capacitors being charged, right? So we have our energy leaving the battery, etc. And so if we took the system, not just what we thought is the system, but the system including the capacitor, the battery, etc., we'd find that our energy is indeed conserved. Okay, so when we were trying to deal with Lagrangian mechanics, and we would use the Euler-Lagrange equation to model a particle's trajectory, we'd end up with a second-order differential equation that would model that trajectory. Now this means that we would, in turn, not only need to know the initial conditions in the position space, so where a particle is, but also its initial velocity as well. Now with Hamiltonian mechanics, we kind of take the focus off of needing initial conditions and initial velocities, and instead focus on something called the phase space. The phase space is the space of position and momenta, and using this idea, we're going to be able to whittle it down from a second-order differential equation into two separate first-order differential equations. So using the phase space, we actually double the amount of dimensions that we're dealing with, which might sound like it's making life more difficult, but in actuality, it'll often make life a little bit easier. So the way that we're going to do this is we'll just assume that we're using a normal everyday particle where the momentum is equal to the mass times the velocity. Okay, so that means that we would have our, say, our Hamiltonian H will be 1/2 m q dot squared plus some v of q, where now the momentum p is equal to mq, and so we'll send q to p over m, and that means we'll be able to rewrite our Hamiltonian H as p squared over, or rather this is our q dots, p squared over 2m plus some v of q. Right, so this is the Hamiltonian we're going to be using when it comes to like phase space now. So let's have a look and try to differentiate our Hamiltonian with respect to position. Right, so if we take our dh dt, or sorry, dq, we'll notice that the first part of our Hamiltonian here has no dependence on the position, and so it'll go to 0. And our second term here, our potential energy, will go to v prime. So we'll have v prime of q. But if we remember that the force, so p dot, is equal to minus dv dq, we'll be able to replace this here with a minus p dot, and so we can say therefore that, dh dq is equal to minus p dot. Okay, and now let's have a look at, we'll just box this here, and let's have a look at the taking the derivative of the Hamiltonian with respect to momentum this time. So this is a little bit simpler. We just use the product rule or the power rule and bring the two down, and we'll get that this is just p over m, where remember we defined p as equal to m times q dot, and so we'll get that the derivative of the Hamiltonian with respect to momentum is equal to q dot. All right, now these are called Hamilton's equations, and they're really handy when dealing with modeling particles and that type of thing. Okay, so now we have a nice little collection of equations. So we have our definition of the Hamiltonian in terms of the Lagrangian, our connection between the derivative of the Hamiltonian with respect to time and the partial derivative of the Lagrangian with respect to time, and our two of Hamilton's equations. Right, so we assume these to be true in one dimension, or our momentum equals mass times velocity, and our kinetic energy equals to a half mv squared. And so we'll just keep it for now and deal with more rigorous derivations a little bit later on. But for now, we're going to be talking about the harmonic oscillator again, and the Hamiltonian that comes with that. So our harmonic oscillator will pop up throughout classical mechanics, quantum mechanics. It's an amazing way of modeling a lot of things. And so we're going to have a look and see how we can model it using our Hamiltonian mechanics. So if we say that a harmonic oscillator has Lagrangian L equal to a half m x dot squared minus a half kx squared, we can use our, we're going to use a little bit of a trick to get this into our phase space, right? So we want it in terms of some momentum p and some position q. Well, we're going to have to do this in a little bit of a different way. So we're going to, let's say, let q equals k times n to the 1/4 power times x. Okay, right. So this means that, therefore, x will be equal to q over km to the 1/4 power. And so x dot will be equal to q dot over km to the 1/4 power. Right, so let's swap this in our Lagrangian, and so we'll get that L is equal to 1/2 m q dot squared over the square root of km minus k over 2 q squared over the square root of km. And this just comes from squaring our x and x dot. And now we'll make another substitution, and we'll say that omega is equal to the square root of k over m. Now these substitutions don't actually change anything, they just make showing, or they make our notation a little bit easier to read. Right, and so looking at our Hamiltonian again, we'll get q dot squared over 2. We'll bring this m inside the square root, and then we'll get m squared over km to be rooted. Similarly, we'll get minus q squared over 2, and bring this k in, and we'll get k squared over km to be rooted. This m will cancel with this m squared. This k will cancel with this k squared. And using our definition of omega here, the square root of k over m, we can say that this is therefore 1 over 2 omega times q dot squared, our Lagrangian, minus omega over 2 q squared. Okay, now we have a kind of idea of our Lagrangian in terms of q now. Okay, so now that we have our Lagrangian, we remember that our Hamiltonian is defined as the sum over I of p sub I times q sub I dot, rather, minus L, our Lagrangian. And in this case, because we're only dealing with one dimension, we'll have p times q dot. Right, so now we just need to make sure we know what p is. But if we remember, we defined p to be the conjugate momentum of some q, which meant that we had to use we would define rather p as, or p sub I rather, as dl dq sub I dot. Right? So this is how we define our momentum. So now we have this, we can say that our momentum is going to be, well, where do we see q dot? We see it here, so we'll bring it down, and we'll realize that this means that our momentum is q dot over omega. Right. So now we can start plugging things into our definition of the Hamiltonian. So we'll say that our Hamiltonian will be p times q dot minus 1 over 2 omega times q dot squared minus, or rather plus, omega squared over 2 times q squared. Okay, right? And now we can factorize these by saying q dot times p minus q over 2 omega plus omega squared over 2 q squared. Right, or this is a q dot here. So using this, we can say that q dot is going to be equal to omega times p, right? By multiplying this equation by omega on both sides. And so we can say that this is therefore going to be omega times p from this here times p minus p over 2, right? From our definition here, or our definition here, times or plus omega squared over 2 times q squared. P times p over 2 will just be p over 2, and when we expand it out, we'll get p squared over 2 times omega. And so we have finally that our Hamiltonian will be omega p squared over 2 plus, sorry, one mistake here. This omega should not be squared in any of these, because it wasn't over there. That was just, I should bring it over. So we'll have plus omega squared, or omega over 2 times q squared. We can factor out the omega 2, and we'll get omega 2 times p squared plus q squared. Right. Now we have our Hamiltonian. Perfect. Okay, so now that we have our Hamiltonian, let's start having a look at what we can do with Hamilton's equations over here. That we assume to be true for this, given that we show that it was true for our, or we showed that it was true in one direction in the last part. Right. So now that we have our Hamiltonian, let's plug it in to our equations. We'll get that dh, partial h, partial q will be, okay, so we only have to deal with this part here. We'll bring the 2 down, and we'll get omega times q, and we know that this is going to be equal to minus p dot. And we'll say that dH dP is going to be similarly, bring the 2 down, we'll get omega times p is equal to q dot. Okay, right. So now we can differentiate both sides of this second equation with respect to time, and we'll get omega p dot is equal to, okay, before we go into that actually, we now have two equations that model how our particle is moving, right? We have mass times acceleration here, so we have our acceleration, our position, and our velocity and momentum here. But if you remember when we were doing our mechanics, or our Euler-Lagrange equations, or our Lagrange mechanics, we were able to say for the Hamiltonian that it would have, if we plugged it into, say, to the Euler-Lagrange equations, or we've shown multiple times that the harmonic oscillator will have q double dot times minus omega squared times q. So now we're going to have to see how we can get this out of it. And it is quite simple. By, just as I was saying, we differentiate the second equation with respect to time, and we'll get omega p dot is equal to q double dot. But notice that we have a p dot up here, so we can sub in this, and we'll get omega times minus omega q is equal to q double dot. Or, finally, that minus omega squared q is equal to q double dot, which is exactly the same as what we got doing harmonic oscillator previously. So that means that we've now used our Hamiltonian mechanics to find the equation of motion of the harmonic oscillator. Okay, so now that we have our Hamiltonian, our equation of motion done by the Hamiltonian method, let's have a think about what this means in the phase space, right? So our phase space we defined as the space with of qi and pi. We're really going to have q and p now, but if we think about graphing this, right? So with one dimension, it's not the worst, or with one-dimensional movement, it's not the worst. So if we have some p axis here and some q axis there, well, we know actually by our Hamiltonian here that it will just move around in a circle. So in reality, what we're going to be doing is, actually I must say, the fact that our Hamiltonian, our energy is conserved, will guarantee that this just moves in a circle. Because there's no, remember there's no explicit time dependence on the Lagrangian. So we'll have that this just moves around in a circle in the phase space. But we can actually kind of, if we take any point here, let's say find this, and we project it down, we'll see where it is in the position space, so along its one axis. And so if we realize that if we were to project all of these up and down, we'll see that it just oscillates back and forth. It will go just along one axis oscillating, which is what we expected for it to happen anyway. So the harmonic oscillator is a particularly simple example, but in general, systems won't move through the phase space so easily and so simply. But the fact that the phase point, it's called, is on a contour of energy. So on one, like this circle here, because our Hamiltonian is conserved, so it could be 5 joules or whatever, it will be one stationary number, we get a circle out of it. And so for any value of the Hamiltonian, the phase space will be on some contour, or which is to say one of these lines. So in this case, this circle here is what we call our contour, and our phase point stays on this line. If our Hamiltonian was larger, we'd have a larger circle, and that would be another example of a contour. But again, this is a pretty simple example. In more general cases, it won't look so elegant. Okay, so now with that example of the harmonic oscillator out of the way, let's have a look at a more rigorous derivation of Hamilton's equations here. So with this, we're going to say we have some Lagrangian L, which is a function of the set of all q sub I e and the set of all q sub I dot, right? And then we have our Hamiltonian, which is defined as the sum over I of p sub I times q sub I dot minus the Lagrangian L. Right, so now we're going to have a look at kind of our variant of the Hamiltonian. So we'll say that we vary the Hamiltonian by delta H, and we'll say that this is therefore equal to the sum over I of p sub I times delta q sub I dot plus q sub I dot times delta p sub I minus delta L. And the Lagrangian being a function of q sub i's and q sub I dots, we'll also have to vary that. So we'll have this as p sub I times delta q sub I dot plus q sub I dot times delta p sub I minus the sum over I of dl d q sub I times delta q sub I plus dl dq sub I dot times delta q sub I dot. Right, so because we're summing over the same index, so we're both summing over I, we can combine these two summations into one giant sum, and by doing that we'll also distribute this minus sign, and so we'll have that this is equal to the sum over I of p sub I times delta q sub I dot plus q sub I dot delta p sub I minus partial derivative of Lagrangian with respect to q sub I times delta q sub I minus dl dq sub I dot times delta q sub I dot. Okay, right. So if we remember our definition of the conjugate momentum, so we said that the momentum p sub I is equal to dl dq sub I dot. And so we can see that this term here is the same as this term here. So this first term with the momentum is the same as this last term because of this here, because of this conjugate momentum connection. So that means that we can therefore cancel each other out because they're taking minus signs, and so we'll have that this is equal to the sum over I of q sub I dot times delta p sub I minus dl dq sub I times delta q sub I. Okay, so now let's have a look at another way of expressing the variations in delta H, or in delta H, which is our normal way of doing it. So we have delta H is the function of q sub I dots and p sub i's, or sorry, q sub i's and p sub i's. We'll have therefore that delta H is equal to the sum over I of dH dq sub I times delta p sub I plus dh dp sub I times, dh dq sub I times delta q sub I and dh dp sub I delta p sub I. Okay. Right, so now we can have a look at grouping things together. So we'll notice that this delta p sub I here, this first term, will share, because of the delta p sub I, we can tell that this must be therefore equal to this last term here. And so we can say that dh dp sub I is equal to q sub I dot. Okay? And likewise, we can say that this first term here must be equal to this second term here, remembering to factor in this minus sign here, or to keep that in mind. And therefore, we can also say that dh dq sub I is equal to minus dl dqi. Okay, so now we have this, and we're almost done. We remember that this, from our time working at the Leonard equations, is nothing more than p sub I dot. I'm going to have to remember to keep in the minus sign there. And there it is. There are our two of Hamilton's equations. They're derived in a more general form. And that finishes our lecture on Hamiltonian mechanics.